self-assembly, self-alignment of plasmonic nanoparticles in liquid crystals. This work is done in collaboration with many people, including Selfalignment at Degens University in China, Eugene Zubaryev at Rice, Chris Schoen, One Park at Boulder, and Pratibha at Raman Research Institute in India. And many graduate students have been involved in this research. I guess you recognize many of them in this picture. I would like to start from some interesting historic background that relates to response of liquid crystals to external fields. So we all know that liquid crystals are very responsive to external electric field, and by applying 1 volt or so, we can simply switch the pixels in liquid crystal displays, and this enables a number of different important applications of liquid crystals. The reason for us being able to switch liquid crystals that easily is because we minimize, when we apply electric field, we need to minimize the electric field term in the free energy, and the electric constants delta epsilon can be fairly large. So just 1 volt of external electric, 1 volt voltage, AC voltage is sufficient to switch liquid crystal displays, right? Now, however, the liquid crystals still poorly respond to magnetic fields, right? Those are diamagnetic media typically composed of organic molecules, and their response to external magnetic fields is fairly poor. Now, back in 70s, Degens had a very interesting idea. So he thought, well, what if we dope the liquid crystals with ferromagnetic particles, and we know that those can respond to external magnetic fields, and hopefully the doped liquid crystals will then have much enhanced response to external magnetic field. He wrote a theoretical paper with Brochard, cited in here back in 1970, and this actually has been realized experimentally many different times, because obviously the ideas of Degens inspired many experimentalists. And back in here you can see 2 papers in 1970, first one, the other one in 1983, in which a system of this kind has actually been realized, right? So the system used in this case was a liquid crystal doped with nanoparticles, rod-shaped nanoparticles, that would have 50 nanometers or so in length, right? And they would be somewhat bigger than liquid crystal molecules, obviously, because, as you know, liquid crystal molecules are in length some 2 nanometers or so, smaller than a nanometer in width typically, right? And so, however, the prediction of theoretical model by Degens was that the nanorods will, or needle-like particles, ellipsoidal particles, anisotropic particles in general, will align somehow with the director, and therefore, if we then apply an external magnetic field, the response to the external magnetic field will be strongly enhanced. So, for example, if we apply magnetic field in a direction that's not parallel to the liquid crystal director, then the rod-like particles rotate in response to external magnetic field, and the liquid crystal director is forced to rotate too, because the orientation of rod-like particles is coupled mechanically to the orientation of liquid crystal director. right? And so, why do I mention this is because today I will discuss in deep details particles of very similar kind, which will also be surprisingly also 50 nanometers or so in length, but we will try to enhance some other properties of liquid crystals, right? Not their response to external magnetic field, but rather how they interact with electromagnetic waves, in particular with light. And this brings me to the slide I would like to show here. So we all know about silver rush and gold rush, and right now in the scientific community we have some sort of metamaterials rush, right? The number of papers published every year is increasing exponentially. Many people get excited, very interested, and although this field overall sort of started in 1999, but now it's really one of the major research areas in physics, engineering, and interdisciplinary science in general. And the idea here is the ability to design artificial materials composite materials which will interact with light and electromagnetic waves in general in a pre-designed, predictable way, right? So originally I was expecting that Professor Ron Shen by this time will give 4 introductory lectures into metamaterials, and so I did not plan having the slides that I will show in a couple minutes, but because he was not able to join us for the ICAM summer school, I'll give a couple slides of introduction to metamaterials, right? So metamaterials are composite materials with structure and composition designed to predetermine their response to in the interaction with electromagnetic waves. Typically, those structural units have size which is much smaller than the wavelengths of light. Typically, at least 10 times smaller, right? So that they appear homogeneous to the waves. The structural units from which they would be built can be thought of as artificial atoms and molecules, right? And having those structural units as artificial atoms and molecules, we then can design materials with predicted and a response to external to the electromagnetic waves, the interactions with electromagnetic waves. So here is a cartoonish representation of how interesting behavior one can obtain if you can control the material response and the index of refraction in particular of the metamaterials. Right? So if we have naturally occurring materials, obviously we know from high school physics, I guess, then refractive index is positive, right? And bending of light at the interface of two media, such as air and some other medium, can be depicted in the form as I show in here, right? So we have some refraction that depends on the refractive index of this medium. Now, however, if the index of refraction would be negative, and for this, the medium would have to have both effective epsilon and mu negative, right? Then the ray of light would be refracted into the opposite quadrant as depicted here, right? And so this is obviously very interesting. You can also see what would happen if you were to insert, say, a pencil or a rod into a medium that has negative index of refraction. Obviously, those have not been realized in the form like this. This is sort of cartoonish representation just to help our understanding, right? So the bending would be fairly different, as you can see here. Now, why are we so excited about metamaterials, right? It's a very interesting concept, and it's probably the first time when we can, as physicists and engineers, think about designing artificial matter, right? Not just simply having to deal with whatever is naturally available for us, but being able to design artificial matter that will interact with electromagnetic waves in the way that we want. Right? This brings an incredible range of untouched fundamental problems, right? Because they have not been explored. For many decades, nobody thought about doing this, right? So obviously, a lot of things can be explored, and there are many untouched fundamental problems. There is also a huge number of potential applications, and in here is definitely not a complete list of them, but in this list you can see perfect lenses that will help to break the diffraction limit and therefore do nanoscale optical imaging with some very simple optical elements like flat lenses. Better optical tweezers, right? So you remember during the first week we discussed optical trapping and manipulation. This would benefit a lot if we were to have better lenses, and that would allow one to manipulate objects with on nanometer scales. One could also design very simple wide-angle beam steering devices, right? Because light could be bent much more easily to larger angles. One can design novel bandgap materials, high-density optical storage. One of the reasons for that is because you can focus light so tightly without worrying about the diffraction limit. Also, stills technology, of course, this is military applications, but nonetheless, it's one of the application areas. Imaging with subwavelength resolution I already mentioned, right? And so there are many, many others, but I'll not go through them in details right now. But probably one of the most exciting applications is the sub-resolution optical imaging, because it would greatly benefit many different branches of science, including biology, material science, and so on and so on. So, what are metamaterials? Let me start from a very simple example that I want to discuss with you. So, if you think about regular materials, then we know that the material response to the electromagnetic waves can be understood using very simple principles about which we learned long ago, right? And we know that we can use Clausius-Mazzotti equation to simply link the atomic polarizability and the dielectric constant of the medium that we deal with, right? And so here is this expression, I guess familiar to you. Now, a question is, if we can design artificial atoms and molecules that would have desired values of polarizability, can we then design the response to electromagnetic waves of those materials to electromagnetic waves, so that they would have desired values of the electric constant at optical frequencies or other frequencies, and also refractive indices, right? But in order to be able to do it, we need to use artificial structure to modify or design the polarizability of the materials, artificial materials that we will be working with. And this would then allow to engineer the macroscopic optical properties, in particular the constants of epsilon and mu. And so in order to be able to do it again, we need the artificial atoms or molecules that would be much smaller than wavelengths of light, and we need to be able to design their electric and magnetic response, right? And so in order to design the electric dipole response, the easiest approach is to simply use the surface plasmon resonance properties, because close to the resonance frequencies, the effective values of the constant would change sign, and so we can have a broad range of those values. Now, in the case of magnetic dipole response, it is a little bit more challenging, but there have been a number of breakthroughs during the last decade or so, and the first approach was proposed by Pendry, is approach to use a split ring resonator, and I'll discuss it in a minute in a bit more details. But there are many other approaches too, which can include, for example, nanorod pairs, the Fishnet structures, and nanoclusters of particles, also the dense dispersions of nanorods, and clusters of particles of different kinds, right? As I mentioned already, we can obtain, for example, negative value of epsilon by using surface plasmon resonance properties of metallic nanoparticles. But in the case of the negative value of mu, one way to do it is to use the split ring resonator, which can provide the strong negative magnetic response, and this is the Pendry's idea, which then results in the effective mu, which is a function of frequency again and again. Because we are close to the resonance, we can have access to a number of different values of mu, including negative and positive. But as I mentioned already, the negative mu values can also be achieved by using dense dispersions of nanorods, pre-designed clusters of nanoparticles, and so on. Now, in terms of achieving negative or other desired values of epsilon, it is more easy. We need to take advantage of surface plasmon resonance, and in particular, for example, if we were to use nanospheres, they have just one SPR peak. For gold in water, that would be some 525 nanometers resonance wavelengths. For silver, that would be at 400 nanometers. So you can see that we can have access to different frequencies in visible spectral range too. For the case of the nanorods, we can have two resonance frequencies the transversal and longitudinal, and the value of longitudinal SPR peak, wavelengths for the longitudinal SPR peak depends on the aspect ratio of anisotropic rod-like particles. Right? And so just to elaborate a little bit more on the possibilities of using metamaterials for the imaging applications, I would like to again give a little bit of historic background. So Veselago, in his paper back in 1968, speculated at that time by saying that if one were to have a medium with negative both mu and epsilon, or in other words negative effective refractive index, then one could compose a super lens from such a medium that would not be subjected to the diffraction limit. The reason for this is that the surface waves are not lost when focusing light using such a super lens, which is not the case for the conventional lenses. Again, the reason for this is that the surface waves or evanescent waves can be transmitted through the system. So they participate in the formation of the image. Now I would like to show some examples of optical metamaterials. So after the strong interest to metamaterials has been attracted by papers by John Pendry a little bit more than a decade ago, many experimentalists started to work on experimental realization of metamaterials. And obviously, since as I mentioned already, we need to compose those artificial molecules and atoms to be of size at least 10 times smaller than the wavelengths of the electromagnetic waves. It was easier to do for microwaves rather than for optical frequencies. Right? And so some of the first metamaterials were realized for microwaves by Smith, and in here you can see the designs proposed by Pendry but realized by the Smith group of different types of metamaterial structures. So the size in here would be some centimeter or so, right? It's easy enough to fabricate them and realize if you are interested in microwave. And indeed, those metamaterials already find practical applications. They are not just simply scientific curiosity, because in the microwave range, it's somewhat difficult to oftentimes it's difficult to have different kinds of optical elements, and then they can be made out of the metamaterials of this kind. Now, when it comes to the optical frequencies, obviously realizing them is much more challenging, because we know that the wavelengths of light and the visible part of spectrum is hundreds of nanometers. So that means these features of interest that we would need to fabricate to obtain the metamaterial response in the optical spectral range, visible spectral range, need to be on the order of 100 nanometers or smaller, right? And now fabrication of some features that would resemble somehow the designs of metamaterials for larger wavelengths are much more difficult in this case. Right? However, there have been a number of approaches again which are which were quite successful in demonstrating metamaterial response in the near infrared and also visible part of spectrum. Right? And so in here you can see some of the designs, so they could, for example, be composed of coupled vertically oriented rods like this, or aligned horizontally, or also having intercalated into each other double split resonators as shown in here, although this is more for infrared part of spectrum. And as I mentioned already, so you can see by looking at those designs, we essentially need crystal-like organization of some structures that are composed of plasmonic nanoparticles, and we need to work with the size of those particles being on the order of 50-100 nanometers in order to achieve this response in the optical or infrared, near-infrared part of the spectrum. And we also need to be able to organize those building blocks of metamaterials into crystalline or liquid crystal-like structures, right? So that would then allow to have materials with pre-designed response to electromagnetic waves. Right, and so in here I show some more examples which again have been done in effort to obtain this metamaterial response in the optical part of spectrum. Some very interesting works done more recently related to the so-called chiral metamaterials. Now one of the most successful metamaterial designs is that based on the so-called Fishnet structure that you can see here, they provide response in the optical IR spectrum. So as you can see in here, the features of the structures are again on the scale of hundreds of nanometers, right? And so all of those materials, metamaterials, have been obtained by some tedious processes of nanofabrication. So it's it's fairly hard to fabricate such metamaterial structures. So one has to use, for example, e-beam lithography in order to be able to generate features with the length scales that you can see in here. Now the question is, how can we go beyond what has been achieved already, right? So one can imagine that nanofabrication is fairly expensive and it does not allow for mass production for any sort of application purposes, right? So if you think about using metamaterials for devices in any sort of applications, manufacturing them this way is sort of limited, greatly limiting the possible applications, right? So the other issue is related to the fact that typically the realized metamaterial structures have two-dimensional designs, right? And much more interesting response can be obtained if one were to be able to design three-dimensional optical metamaterials. There is also limited or no tunability, right? And if one were to read, for example, a science perspective article by the three co-authors you can see in here, who are some of the best experts in the field of optical metamaterials, you will see that they say that, however, for applications to come within reach, several goals need to be achieved, and those include reduction of losses, right, because metamaterials are fairly lossy, three-dimensional rather than planar structures, and also ways of mass production of large area structures, right? And so, in terms of tunability of the properties of metamaterials, there have been some progress recently, and in some of the approaches, people also utilize liquid crystals to be able to do it, because, for example, in the case of fishnet structure, the cavities in the fishnet structure can be filled in with liquid crystal, and this allows for some tunability by applying external fields or optical tunability. Now, obviously, it would be great if we could achieve self-assembly of optical metamaterials or other types of metamaterials, metamaterials for infrared part of spectrum too, and this is, however, presently a great challenge. So we can use self-assembly to obtain crystals, right? And so in here you can see a beautiful crystalline self-assembly of gold nanorods. Yet this would not give you a metamaterial immediately, right? Because you have little or no control over how this assembly proceeds, and also you would not be able to do it with all kinds of nanoparticles, all kinds of artificial atoms and molecules that you might want to design. And also you would not be able to switch or realign the building blocks of such structures by external fields. So obviously just crystallization of monodispersed colloidal particles like gold nanorods wouldn't be sufficient to achieve those goals. Now one could think about liquid crystallization of the gold nanoparticles, like rod-like nanoparticles, right? And however, we know that the liquid crystalline self-assembly, even in the simplest case of rod-like colloidal particles, can be achieved only for some particles of high enough aspect ratio and also at high enough concentrations of those particles, right? And so there is a very simple relation for rigid rod-like particles that one can use to estimate and see that this would be impossible to do for pretty much all particles of interest, right? So for the critical concentration at which we, so as you know, just to remind you, if we increase concentration of rod-like particles at some critical concentration, we can have spontaneous formation of nematic-like liquid crystal state, and this happens to maximize the entropy of the system, of the particles, including the translational and orientational entropy accessible to those rod-like particles. Now, so the critical concentration at which such a transition can occur is 4 ratios of diameter of the rods to the length of the rod, right? And if we simply take rod-like particles similar to the ones you can see in here that have very interesting response and surface plasmon resonance peaks both longitudinal and transversal in the visible part of spectrum, we realize that the aspect ratio of 2 or 3 is not large enough for us to achieve the liquid crystalline state even at very high volume fractions of rod-like particles. So it's pretty much impossible, right? Because just simply estimating what concentration you would need, you realize you are not able to achieve it, right? And so and in addition, typically we use either polymer brushes or charge stabilization to stabilize such particles, which further increases their diameter, effective diameter, and makes it even more difficult to obtain liquid crystallization of such particles. And as I mentioned already, most interesting particles, rod-like particles in particular, would have the aspect ratio that would not be high enough to achieve the liquid crystal state. But now we can sort of explore the Degens idea, where he simply used a liquid crystal formed by some molecules, like organic molecules that we use in liquid crystal displays, and we can then incorporate particles such as gold particles or silver particles into this liquid crystal medium, and provided that we are able to achieve exactly what those experimental groups that I showed before were able to achieve for magnetic needle-like or rod-like particles, we actually should have a very interesting system from the standpoint of view of metamaterials, right? Because in those papers, what has been realized is the particles are aligned with liquid crystal director, right? They respond to external magnetic field, but they do not aggregate. They do not form any sort of clusters that would then, cause phase separation of those nanoparticles from the liquid crystal, right? And so the nanoparticles that have been used in those studies were 50 nanometers in length. That's pretty much ideal for our purposes too. And so the question is, how can we do it, and is it easy to do or not? And I'll discuss this in more details. In particular, I will discuss all points mentioned in here, how we can achieve alignment of plasmonic gold nanoparticles, what kind of properties we obtain for the composite systems of nanoparticles doped into the liquid crystal, and also how we can use the switching by external magnetic fields to be able to control those properties. Right? So, but the main issue is related to dispersion. Right? Somehow in those experiments back in 70s, people without too much effort were able to disperse them. Right? And of course it always depends on the type of nanoparticles you use. Some are easy to disperse, some are much more difficult to disperse. Right? But in terms of the dispersion of colloidal particles in not just in liquid crystal media but in fluids in general, one has to overcome the action of van der Waals forces, right? And for this, one can use either charge stabilization or can use some stabilization with polymer brushes. I guess you remember from the lectures of David Pine about different approaches of achieving it. So this example you can see in here is showing us how one can kinetically stabilize a dispersion of colloidal particles in some solvent. So there is a kinetic barrier which is due to charge stabilization, that prevents particles from coming close enough where the van der Waals interactions would cause irreversible aggregation, right? As long as we can keep them far enough from each other, then they will not aggregate. And in order to be able to keep them far enough from each other, one needs to produce a kinetic barrier that can be obtained by either charge stabilization or stabilization with coating the particles with polymer brushes and so on. And then this approach can be applied to a number of different gold or silver nanoparticles. What's interesting is there is a huge number of different shapes that the gold and silver particles can have, and in here is probably incomplete list of all of them, right? Later on we'll see that the shapes are important from the standpoint of view of the design of metamaterials that we will discuss later. Now, in terms of incorporating the particles into liquid crystals, the particles can be linked to liquid crystal molecules, and this can be helpful or not very helpful from the standpoint of view of their stabilization in liquid crystal media, but this part we'll again discuss a little bit later, right? So now the first examples I will discuss will be related to rod-like particles, and in here you can see examples of different particles having rod-like and wire-like shapes that are made of gold, and some of them have been synthesized by Julian sitting here. Now a question is, if we incorporate those particles that we know we can stabilize by means of charge or polymer stabilization and some other solvent, what is different when we incorporate those particles into liquid crystal from the standpoint of view of their colloidal stability, right? And so we know already from the previous lectures that the liquid crystals can, that the colloidal inclusions can set boundary conditions for liquid crystal molecules. And so in here I'll just show a simplest example where the boundary conditions are vertical, right? And so if we have those vertical boundary conditions, then the molecular alignment around such a particle looks like that around the point defect that is shown in here. Now, this point defect has a topological charge +1, and we do need to conserve topological charges just like we need to worry about conservation of electrostatic charges in electrostatics. And so, indeed, when we incorporate such a particle into liquid crystal, we can see formation of another point defect of -1 topological charge and distortions of liquid crystal optical axis around it. Those are all elastic distortions that cost a lot of elastic energy, right? And this is how such a particle would look like between cross polarizers and analyzer, right? So the bright regions are due to birefringence of liquid crystal in the regions where optical axis is at some angle not parallel or perpendicular to polarizer and analyzer. And then we can have a number of other situations, like for example disclination rings, like the ones of half integer -1/2 disclination ring shown in here, because a loop of -1/2 disclination is equivalent to -1 point defect, and therefore again we can have topological charge conservation in this case. Now you can notice in here that we have either dipolar or quadrupolar symmetry in the structures that have been formed, and therefore if we put such particles, many of them, into the liquid crystal medium, we realize that they interact with each other to minimize elastic energy, right? And so you can then have either linear chains, which are lined parallel to the far-field liquid crystal director, or you can have linear chains which are at some angle, in the case of particles with quadrupolar symmetry of distortions of the molecular alignment around them. And so what does this mean from the standpoint of view of achieving the goal of alignment of the particles without causing aggregation is that the liquid crystal elasticity makes it more difficult, right? From the standpoint, the dispersion of particles and nanoparticles in particular in the liquid crystal medium, because the distortions, elastic distortions like those you can see in here, will cause the particles attracting to each other at some angle, coming in contact and eventually forming big chains that can aggregate, that can separate out of liquid crystal. And obviously this will be also true for particles of other shapes. Now, how can we obtain the colloidal dispersions in liquid crystals that are not susceptible to aggregation? Well, one approach we used recently was to use so-called smectic liquid crystals instead of nematic liquid crystals. And the reason is that in this case, the layered structure of smectic liquid crystal helps to stabilize those colloidal inclusions, because whenever the particles happen to be within the same layer, they repel each other because the symmetry of distortions around them in this case is quadrupolar. So quadrupolar particles tend to attract each other at some angles which are intermediate between 0 and 90 degrees, right? And so in this case they would be repelling each other. However, if the particles were to be found in, at some angles between the interparticle separation vector and the plane of the layers, then because the particles are in different layers, they cannot easily penetrate through the layer structure, because this would require creation of dislocation loops, and therefore they can be stabilized by such a layer structure. So interaction between such particles is essentially similar in this case to the interaction between dislocation loops, right? And so they would not attract to form aggregates. So therefore one could load much higher concentrations of particles into liquid crystal medium. Now the other interesting observation of experimental observation we had was that if we had small enough particles, they also do not aggregate, right? So this is demonstrated here by some of the experimental pictures obtained by use of cryogenic, by use of free structure transmission electron microscopy. And so when the particles had the size of only 2 nanometers or so, and they are dispersed in the liquid crystal medium, such as cholestatic liquid crystal, you can then zoom in the image and see individual particles that do not aggregate, right? And the reason in this case is that the particle size is fairly small, so that they do not distort the reactor field that much, right? And so therefore the cost of elastic distortions, even in nematic or cholestatic liquid crystal, can be small enough is too small to cause the strong interaction between particles that would for result in formation of some chains or other types of aggregates, right? And so we can see that we can achieve dispersion of small particles in nematic oculostatic liquid crystal medium, provided that the cost of elastic distortion that they induce is smaller than K Boltzmann T. Right? Now, in yet another approach which has nothing to do, so in here those were gold nanoparticles, right? But a very different type of particles can behave in a similar way. And so in here you can see rod-like bacteria, Pseudomonas aeruginosa. And so we do not run movies, but if you were to be able to run movies in here, I would show you how those bacteria swim along the direction prescribed by the director field, along the director field. And so what we have in here is a liquid crystal formed by stretched DNA molecules, and the rod-like bacteria behave similarly to the rod-like colloidal inclusions, right? Now, however, the distortions they produce in the liquid crystal made of DNA are not that costly from the standpoint of view of elastic free energy, so that the interactions between them can be easily prevailed by motility, right? And so again, we do not have aggregation, although we do have alignment of those rod-like bacteria. And this is very interesting. So if we were now to be able to achieve a similar kind of alignment of gold-like particles in liquid crystal, that would be very interesting, and from the standpoint of view of forming metamaterials out of them. So now I mentioned already what we have in here is essentially alignment of rod-like bacteria, but we do not see much of their aggregation, right? So why do we have alignment? The reason is very simple. The rod-like colloidal inclusions that impose tangential boundary conditions on liquid crystal director distort, in the case if they align parallel to the far field director, will distort the director field only at the edges of those rod-like inclusions, right? While there would be distortions all the way along the length of the rod if you were to have the alignment at some angle with respect to far field director, for example, perpendicular to the far field director. And so therefore, this type of alignment corresponds to minimum elastic free energy, right? And so I would like to show you in just a couple minutes from now that this liquid crystal elasticity is strong enough to align rod-like particles, but the interactions, elasticity-mediated interactions between them, the colloidal rod-like particles, are weak compared to K Boltzmann T, so that you do not observe aggregation of those particles, right? And so the system that we work with is the gold nanoparticles that are stabilized by CTAP, and I'll show that the liquid crystal, the so-called lyrotropic nematic liquid crystal, can be used to align such rod-like colloidal inclusions. It can be achieved both in the nematic liquid crystal phase, where the building blocks of the liquid crystal, the micelles that have cylindrical shapes, are all aligned in the direction parallel to the liquid crystal director locally, right? And they impose unidirectional alignment of the colloidal gold nanorods, as shown in here. And this can be also achieved, such unidirectional alignment can be also achieved in columnar hexagonal liquid crystal phases, where the rod-like cylindrical micelles, in addition to aligning along the liquid crystal director, also form hexagonal lattice in the plane perpendicular to the micelles, right? So in this system we now have, in addition to orientational order of the micelles, we have also two-dimensional translational positional order of micelle. However, this system imposes only orientational ordering of the rod-like inclusions of colloidal gold nanoparticles. And so the reason why we can achieve alignment of such rod-like particles we have seen already, because the alignment of rod-like particles parallel to the director minimizes elastic free energy. Now, what about the interactions between the particles? Right? So obviously those regions at the edges of rod-like particles, they look, especially if we have spherocylinders, so the cylindrical particles are capped by some semispheres in the end, and those seem to be similar to the gold nanoparticles that we deal with. So we realize then that elastic distortions are very similar to those that we have in the case of a colloidal sphere of similar radius as the radius of this cylindrical nanoparticle. Now, if we disperse them in a lyotropic liquid crystal, we know that lyotropic liquid crystals have fairly low values of elastic constant, which are typically smaller than 1 piconewton. And the elastic distortions that we can see in here are caused by surface anchoring, right? So the reason why we have elastic distortions in the bulk is because the surface boundary conditions are such that the director aligns parallel to the surface of the particle, right? And so we can estimate, however, the surface anchoring cannot be infinitely strong, right? So we can estimate the surface anchoring energy, overestimate as W r squared over 2 for such a particle. And if one takes, and now because the surface anchoring is the cause of elastic distortions in the bulk, this is also an overestimate of bulk elastic energy, right? Because the energy, the overall free energy, which is sum of elastic energy and surface anchoring energy, has to be minimized. So the maximum elastic energy cost is therefore of this value too, which we can estimate, and we realize that it's comparable to K Boltzmann T. And therefore the elastic distortions caused by such particles should not cause aggregation. While if we estimate the elastic free energy difference for different orientations of the rod-like particle with respect to the far-field liquid crystal director, and for this we can simply use the expression that was obtained by Degens and Brochard back in 1970, or somewhat more recent theories. Then what we realize is that for the particles with a size comparable to what we use in experiment, we have the elastic energy difference as a function of angle theta is of the order of 5 to 10 to power minus 19 theta squared joules, which is fairly larger than K Boltzmann T, even for rather small angles of theta. And therefore, in this system that we deal with, we have something similar to what was realized based on idea of Degens for the magnetic nanoparticles in liquid crystal. In particular, the liquid crystal elasticity enables alignment of those particles without promoting their interactions to form irreversible aggregates, right? So now what do we have in terms of the optical properties of the rod-like particles in the crystal medium? So first, let us see what type of response we have if we disperse such particles in an isotropic solvent. And so in this case, we can see the two surface Plasmon resonance peaks for the particles, and those peaks are in the places predicted by theory for the particles of given aspect ratio, and you can compare the experimental and computer simulated results, and the resemblance is fairly good. So indeed, as I mentioned already, for the particles of this given aspect ratio, we did expect the longitudinal surface Plasmon resonance peak close to 670 nanometers or so, and this is indeed observed in the experiment, right? So if we take a look at the particles that would be imaged by means of transmission electron microscopy, you can see that the aspect ratio is roughly 2.5, although the distribution is somewhat broad. For this distribution of aspect ratios, we indeed expect the surface Plasmon resonant peaks in the places where we observe them. Now, if we, however, obtain free structure transmission electron microscopy images for the liquid crystal sample with incorporated rod-like particles, gold nanorods, what we see in this case is the replicas corresponding to the rod-like particles that are all aligned in the same direction. And so this already tells us that we do have unidirectional alignment of gold nanorods. And this is further evidenced by the optical studies, right? So now for the sample which I just showed with liquid crystal that contains incorporated rod-like particles, we now still see the two peaks corresponding to transverse and longitudinal peaks, surface Plasmon resonance peaks, but we also see very strong polarization dependence of the surface Plasmon resonance spectrum. And so in the plots of extinction versus wavelengths, we can see that if we change the polarization of detected or incident light, the SPR spectra are strongly dependent on polarization. And the color of the sample also depends on the orientation of polarization of the light which we use to look on it, right? So in here you can see the color of the sample for the polarization orientation corresponding to polarizer being parallel to the director and then orthogonal to the director. The SPR spectra that we obtain also match quite closely the computer simulated results, right? That you can see in here. Those results were obtained for orientational order parameter of the rod-like particles equal to unity. Obviously, in the real experiments, the orientational order parameter is lower than unity, and so therefore we have some small differences. But from experimental data, similar to the ones you can see in here, we can also determine the orientational order parameter of the rods, and for the particular results that I show in this graph, one would obtain the orientational order parameter on the order of 0.8. The orientational order parameter can be also calculated based on freeze fracture transmission electron microscopy images, and it's in agreement with those values. So the SPR spectra and also the freeze fracture transmission electron microscopy images demonstrate that we have alignment of rod-like particles, right? But the question is, can we also switch orientation of gold nanorods by applying external fields, right? And the answer is yes, we can do this. So in here you can see the SPR spectra similar to the ones I showed in the previous graph, but now they correspond to a sample alignment of which has been controlled by applying magnetic field. And so the applied magnetic field reorients the liquid crystal director, and then the rod-like gold nanoparticles follow liquid crystal director. So you understand that the gold nanoparticles are not ferromagnetic, right? So they do not respond much to external magnetic field, but since we can realign liquid crystal director, we can therefore change orientation of incorporated rod-like gold nanoparticles. And so if we take the SPR spectra experimentally for orientations of director parallel and perpendicular to the polarizer, we can see the individual transverse and longitudinal peaks separately in the two cases. And so by applying external magnetic field, one can simply switch the liquid crystal director between the two orientations and also achieve fairly uniform, very good alignment of both liquid crystal director and incorporated rod-like nanoparticles in the liquid crystal sample. So those data again closely match the computer simulated results, and they show that one can use external magnetic field for alignment of rod-like nanoparticles in the liquid crystal medium, and also realignment by changing the direction of applied external magnetic field. Now the question is, how do we relate those properties that we have measured so far experimentally, which is extinction in those two cases, and compare them to computer simulations? How can we relate them to some parameters like dielectric constant or the refractive index of the medium, right? And so right now we have the extinction versus wavelengths data similar to here, but one can use effective medium theory and recalculate based on those data and similar ones to what we did all the time in computer simulations. We can then obtain the effective refractive index as a function of wavelengths, and this can be done for both real and imaginary parts of the refractive index. And so for the experimental results that we have discussed so far, the change of effective refractive index is fairly small so far, right? So we did not get anything like minus 2 or something like this. But we can see that the effective refractive index of medium with incorporated nanoparticles is different than that of pure liquid crystal. So the liquid crystal with which we dealt was lytropic liquid crystal, which is water-based, and the refractive index would be close to that of water, right? But you can see that, so would be on the order of 1.34, 35 or so. But you can see that at the wavelengths close to the longitudinal SPR peak, we can see that the refractive index is substantially lower, right? And so indeed, we do have some effective medium with effective parameters, refractive index and the electric constant, different than that of the individual components that we use for this composite medium. And so you can also see the imaginary part of the effective refractive index, which tells us about absorption, and it's also fairly large, close to this wavelengths, obviously. So this tells us that there are some losses. Now, a question is, how could we increase the value of refractive index, the change of the refractive index? So for this, one would have to increase the concentration of incorporated nanoparticles, which is somewhat challenging because as you increase the concentration of gold nanorods, their stability will not be as good, and I'll discuss this in a couple of minutes from now. But one important thing I want to mention is that you can see the dependence on polarization, right? And so for those of you who work with lytropic liquid crystals, you probably would know that birefringence of those media is very small, much smaller than of the order of 0.01, right? So it's 10 times smaller or so than the birefringence of liquid crystals we use in displays. However, you can see that we have been able to enhance the effective birefringence of the liquid crystal medium with incorporated nanorods quite substantial, orders of magnitude. Although we did not succeed with changing the effective refractive index that dramatically, right? The absolute values of refractive index that dramatically. Now, as I already mentioned, the challenge related to further increasing the change of effective refractive index due to incorporated nanoparticles is related to their stability. And so if we have small concentrations of nanoparticles, way below 0.1% by weight, then the stability is very good. Of course, the extinction and all the parameters of interest increase with increasing concentration, but then stability becomes worse, and one can only work with those samples for a fairly short period of time. However, a good thing is that even if the samples become not very stable over a long period of time, one could say think about polymerization, obtaining films, polymer films out of such liquid crystal, so that the problem related to long-term stability of those colloidal dispersions could be mitigated or avoided. Now, the images I wanted to show in here are not maybe clear because of the lightning due to this projector, but I also wanted to show that we can align those nanoparticles not only in the regime when we have fairly high concentrations, but also in the regime where we have very dilute concentrations of nanorods. And so those are the dark field images, and we had some introduction to dark field microscopy during the first week. So as you remember, in the dark field imaging you collect on the scattered light coming from the nanorods, and because the nanorods are aligned, it's strongly polarization dependent, as you can see from the scattering data shown on this graph. And so indeed, as we change polarization from parallel to perpendicular to the liquid crystal director, those bright spots corresponding to individual nanorods change the brightness, and which tells us that we have aligned also the nanorods in a very dilute dispersion, right? Now, the question is, can we go beyond nanorods and nanospheres in terms of the design of metamaterials based on liquid crystals? And the non-spherical and non-rod-like particles are very interesting because, for example, triangular platelets can have very sharp features like those in the corners that provide highly enhanced surface plasmon resonance. And we have seen from Clayton's presentation that we can align platelet particles, polygonal platelets as well in the liquid crystal medium. So that means we can predetermine their orientation with respect to the far-field liquid crystal director. But we have seen that if we deal with fairly large particles, the particles that have, say, the platelets that have micrometer or so in the thickness and couple micrometers in the lateral dimensions, then those particles tend to interact with each other, and they form some structures. So here's an example. I hope you recall the presentation from 2 days ago or so. So this means they, just like colloidal spheres, they interact with each other to minimize the elastic free energy. And this might be interesting and useful from metamaterial application standpoint of view too. However, if one were to have those particles made out of metal like silver or gold, this would not be good because all the beautiful features, surface plasmon resonance properties would be lost as soon as we form the aggregates. Of course, if we were to have the nanoparticles somehow incorporated into the body of such platelets, say if we were to have some rings formed on such platelets, this might be very interesting. However, we can see from this that again we need to deal with elasticity mediated interactions that promote aggregation of the particles, right? Tend to promote aggregation of the particles and formation of some structures. Now, if we were to deal with the gold nanoparticles of shapes that are much different from rods and spheres, such as platelets, triangular platelets you can see here, or even the so-called nanobursts that are pretty much platelets that have very interesting, sharp, irregular features in their periphery, or the so-called nanostar fruit particles that you can see here. They are all very interesting from the standpoint of view of their surface plasmon resonance properties. However, as we incorporate them into liquid crystal, we do have to deal with the same issue, right? How do they interact with each other, or do they form aggregates? Do they form some self-assembly structures, or are they just simply dispersed in the liquid crystal medium, so that liquid crystal provides alignment of those particles without causing their aggregation? And so in the case of polygonal platelets of regular shapes, such as the triangles, hexagons, and nonagons that you can see in here, we have been able to explore what are the possible scenarios in this case too. And so what we observe is that in thermotropic liquid crystals, the common observation is the vertical alignment of the liquid crystal director to the surface of the platelets. And so in this case there is some disclination loop similar to that that we saw for the spherical particles running in the direction in the plane perpendicular to the far-field director. However, if we incorporate those particles into a lyotropic liquid crystal, in this case we have tangential surface anchoring for the liquid crystal director. And so what we observe is that the platelets that have on the 5 nanometers in the thickness or so tend to align with their large area faces parallel to the far-field liquid crystal director. Although because of the very thin thickness of the cell, one can observe random orientations of the particle with respect to the axis perpendicular to far-field director as shown here. And also they can freely rotate around the symmetry axis provided by the liquid crystal director, far-field liquid crystal director. So in this particular case, as I mentioned already, the particles were very thin, and so therefore we can again obtain this type of the alignment in the liquid crystal sample without observing much of aggregation of the particles. So I guess I had some other story to tell, but we probably ran out of time. So I will skip this part, which was on the optical control of alignment of the nanoparticles and azicolloidal particles in liquid crystal. But I would like to conclude that liquid crystals are media that can provide self-alignment, self-positioning, and also optical, electric, magnetic, and other types of control of alignment of different types of plasmonic nanoparticles that are of interest for metamaterial and other applications. And if this would be of interest, some of the things we discussed are also in those papers. Thank you.